So this is going to be part 2 of our weekly webinar series on functional aspects of machine safety. This being part 2, hazard recognition and performance level. Today we're going to talk about some of the ways to find hazards on machine and recognize them. And then once we've identified what those hazards are, how can we determine what performance level we need to safeguard those hazards? So when we're looking at hazard recognition performance levels, a lot of time we're going to run into the term risk assessment. This is the type of thing you're going to do when you have a machine. You need to determine what risks are present, what hazards are present, what is an acceptable risk. All of these things go into a risk assessment. And these are the guidelines that we tend to go to when we look at doing risk assessments and hazard identification. We've got ANSI B11 has a standard on risk assessment. These really aren't standards as more as they are procedures and guidelines. EN ISO 12100-1, safety of machinery. EN ISO 14120 run, principles of risk assessment, and then RIA CSA Z4334 and Z432-04, industrial robot systems, and then safeguarding of personnel, general safety requirements. So, in principle, zero risk is not possible. Regardless of what we do to a machine, the prospect of making it 100% foolproof safe really does not exist. So what we have to do is we have to find a way to minimize that as much as possible. So the purpose of a risk assessment is to evaluate the potential for any type of adverse effect to an individual so that the measures taken can be prioritized and in proportion to the risk imposed. So the greater the risk, the greater the safeguard we need to take. To prevent access to the hazardous point must be interpreted to mean that the residual risk, meaning the risk that we have said is acceptable, is reduced to an extent which is generally acceptable to the operator or anybody involved in that machine. A risk is acceptable if it is accepted by a free and willing individual in question after all aspects have been considered. An acceptable risk is going to be reached by consensus by those responsible for establishing policies reflecting subjective and social viewpoints. So this is going to be normally in a standard type risk assessment. It's not going to be one person on their own doing this. You're going to have engineers, you're going to have maintenance people, operators, shift supervisors, anybody who has any input on the operation of this machine and any tasks that are generally associated with it. We need to get their input on all of this to see what is the normal operation of a machine like this. So how can we get rid of these risks once we find them? Well, the hierarchical method would be to start from the top and move down to the bottom by effectiveness. So first, eliminate it by design. If we can get rid of that risk completely, take that hazard completely out of the machine, obviously that's the best way to do it. Then we don't have to worry about it anymore. We can control access to exposures by safeguarding. That's going to be something like light curtains, multiple light beam devices, safety scanners, hard guarding, interlocked doors, things of that nature. The next one down the list would be to provide other safety measures like awareness barriers, signals, you see the caution tape on the floor, signage, any type of warnings. And then we go down to administrative controls, procedures, training, personal protective equipment. These are the least effective, but the easiest to do. So we see our risk level is indicated by the red arrow here. And this would be our risk without any safety measures, the far end of the spectrum, an unacceptable amount of risk. This would be our maximum permissible amount of risk, much farther down the spectrum. So this represents the amount of reduction we need to do to make this an acceptable risk on this machine. We have our part that we can design out of the machine, and then the residual amount needs to be safeguarded with either barriers, AOPDs, light curtains, things of that nature. That leaves us with our remaining risk, which we then have to determine if it is an acceptable amount or not. So when we're looking to find these risks or these hazards, the simple way we do it is to remember the term auto. around, under, through, or over. So if we have a machine that has guarding on it or a machine that doesn't have guarding on it, we need to be able to establish what is the risk. Is it a spindle? Is it a press opening and closing? Is it a robot stacking pallets? Something like that. So can we go around, under, through, or over any of the barriers or barriers that may not even be there and reach this hazard? If we can, then that is a hazard we need to safeguard, and we need to come up with a way to do that. So according to the various standards we have, CSA, ANSI, OSHA, they all have a little bit different specs, and we'll go into that more in the next webinar, which is safety distance calculations. But we'll touch on it a little bit here. So if we are 1.2 meters off of the ground with a maximum opening of 6 inches, which is mostly for hard guarding, 12 inches usually for AOPD devices, then that gives us a distance of 3 feet that we're allowed to be away. If we are below that, that drops us, I think, to 4 feet. And then depending on openings and resolution of the light barrier or the guard, this could also be a hard guard. The same things would apply. So this is something you may or may not have seen. They're pretty common. It's called a gotcha stick. Lots of people make these. They're usually just handouts that safety companies give away. And it's got all of these notches on it. And basically what it says is if you have guarding in place, or maybe there's not guarding in place, if you can reach the hazard with this stick, that's not a good thing. So we go to a 6-inch maximum. Anything past the 6-inch maximum automatically goes to a 31.5-inch minimum distance you have to be away. So that's as far as the stick will go to. Usually it only goes to this, the 2 1/8. So if you have one of these sticks, sometimes OSHA will have these with them when they come in and do a check. They'll check to see if they can reach hazards with this stick. If they can hit it with this stick, then you're in trouble. Gotcha. This is another kind of example of the slide we had previous to that, the last one, showing 1.2 meters, or we get a 48-inch. Actually, I think this is it. So 48 inches would be the safe distance. Yeah, on this height. 48 inches would be the safe distance on a 0.9 meter. 36 inches is the safe distance on a 1.2 meters. It's a little confusing, but believe me, it's true. So we have depth of penetration, 48 inches on this. Depth of penetration here is 36. So once we've seen these hazards and we know what they are, what are some of the other resources we have to figure out how we can effectively guard these? And some of the generic ones we have are OSHA 1910 Subpart O, which is the machinery and machine guarding standard. It's pretty vague. There are some specific things in there, but they're kind of to niche type of manufacturing environments like woodworking or printing and stuff like that. But they're not real specific. We have R1506, which is just for robots. It also has a lot of other standards in there that are applicable to other fields other than just robots, but this is specifically a robot standard, but a lot of good information inside of there as well. And then for our neighbors up north, we have CSA Z432-04, Safeguarding of Machinery Standard, which is not a law, but it is what all of their safety standards, all the provincial safety standards are based off of. But what we also have is we have ANSI machine-specific standards. These are similar to CSA standards, as in they're not government standards, they are not the law. However, OSHA can refer to these under one of their general clauses saying that the machine has not been made safe based on this ANSI standard. And what you'll also find is that these ANSI standards will be tailored to a specific machine type as well as specific industries. So you may have a machine that you think has lots of hazards involved with it that you have to hard guard or maybe do AOPDs with, and it's just going to be a real bear to get it done. You read the ANSI standard, and you'll find out that this type of machine in this type of an instance can have this hazard unguarded as long as there are certain provisions taken. So there's a lot of very specific information included in these that is very, very valuable and can save you a lot of a lot of time. The only downfall to the ANSI standards is they do cost money. Each one of them you buy costs money. You can't buy a blanket ANSI standard. There's too many of them. So if you are in a specific machinery environment, it would definitely behoove you to try and get your hands on that ANSI standard. They're not too expensive. They're usually 30, 40, 50 bucks, something like that. But it's a lot of very valuable information. So once we know we have the hazards, how do we find the right protection system? Well, we do our risk assessment after we've found our hazards. What are the dangerous movements? What can happen during a normal operation? And what can occur during the setup and maintenance? As we said before, when you do a risk assessment, you need to have everybody involved with that machine there. You need to be able to talk to the maintenance people. You need to be able to talk to the operators, because everybody does something different with the machine. So you need to find out what tasks are involved that they do on a normal basis that could get them injured. Then we can start looking at, well, what measures can we do to negate these risks? So we have fences and sheet metals, detection, which would be our AOPDs, light curtains. Evaluation would be the safety relays that would be connected to these light curtains and door switches and things of that nature. So for every one of these individual safety devices that we come up with, we have to look at the function of that device and calculate the PFHD for all the components that are part of the safety functions. And then we get the sum of the PFHD, and we can check that against the required level and see if that is met. And if not, we can change our components, and then we can calculate that again. And we'll show you how to do that in the next couple slides here. So the hazards and their effect can be best identified by analyzing tasks. So there's a couple different ways you can go, and you can do these risk assessments on a hazard-based assessment, or you can do it on a task-based assessment. And we found that task-based assessments seem to be the most beneficial and the easiest to do. So you can look at the individual tasks that each person does, maintenance and operators, as well as just people who walk by the machine, and see where it is that they come in contact with the machine during their normal task and how we can safeguard that. So when we do a risk assessment, the way we calculate our risk at the end is that the risk is related to the hazard under consideration, or the risk related to the hazard under consideration is a product of the severity of the possible harm, the probability of that occurring, the frequency of your exposure to that harm, and the possibility of avoiding or limiting it. So our risk equals SFPA, so severity, probability, frequency, and avoidance. So when we look at risk elements, as we said before, how bad is it? As you see in the first picture, that would be very bad. Second picture, not quite as bad, but still not very good. So slight, severe, is it a recoverable injury? Are you losing a digit? Are you losing an eye? How often are you going to be exposed to this hazard? Are you going to be in this dangerous area very often? If you're in there, how long are you going to be in there? For a short duration or for a long duration? And then how likely are you to be able to get out of the way of this hazard if it were to come in contact with you? Possible, rarely possible. A lot of that's going to depend on the speed of the hazard. So the easiest way to calculate this with our risk, severity, exposure, and avoidance, in my opinion, the easiest one is the EN ISO 13849-1 out in 2006, the performance level. This is the European norm standard. Here in the United States, a lot of times we use category levels. People are starting to use SIL levels now a lot more, which is safety integrity level. In Europe, we use mostly performance levels still. So we have our severity, slight, reversible, severe, irreversible. And sometimes there's a little bit of overlap here, and a little bit of discretion is needed. For severe, we normally look at loss of arms, death, and eyes. Based on this standard, loss of a finger still, I still believe, ends up as S1, which is slight, although it doesn't seem like a very slight injury to the guy who lost his finger. Frequency, rare to often, frequently to always, and then possibility of avoidance. So if we follow this chart, we can say it's severe. We're already automatically at performance level C. No matter what else we get, we can't go anything below performance level C on our control system. And then if we start with S1, the worst we're going to see is a performance level C. So very easy flow chart to follow, quick and easy way to figure out what your risk is going to be. CSA has a little different version of it, risk reduction index, basically following the same type of path though. Severity of the injury, exposure, and avoidance, they just say it a little differently. And then we have safety integrity level, which actually puts a number to each one of these, which you then add up, and that number determines what type of safety integration level is necessary. So this is an example of a risk assessment sheet using safety integration level. So you have death, losing of an eye or an arm, would be SIL 4, or severity 4, which puts you at a minimum of SIL 2 no matter what else you get. So you have these numbers that are assigned to each one of these levels, frequency, probability, avoidance, and severity. Each one of these gets a number value. Those are added together. And then as you can see here, class C1 in the middle. Wherever you fall within that, that determines what your SIL level is. So as we saw this slide before, at the bottom we talked about, well, we need to calculate the PFHD for all the components in this to see if they fit that safety integration level or performance level or safety category, depending on which standard you're going by. So these are some of the terms we're going to be talking about. MTTF, mean time to dangerous failure. Basically, how many times this piece of equipment can cycle before we can expect to see 10%. I'm sorry, that's the next one. Before we can see a failure. B10D, number of actuations of mechanical parts till 10% of the test components have been failed dangerous. Common cause failure. Our diagnostic coverage, which would be the quality of the failure detection. Ideally for Cat 4, SIL 3, PLE, we want 100% failure detection capability, very high. Time of intended use. This is the one we're going to be focusing on, probability of dangerous failure per hour. And then performance level is what we get when we take all the calculations from these together. So for simple devices requiring a test unit, the PFHD has to be calculated by category, mean time to dangerous failure, diagnostics coverage. And for that we can look at EN ISO 13849. For mechanical components provided with a B10D value, which normally is going to be provided by the manufacturer, the MTTF has to be calculated using the number of actuations per year. So the example for something like this would be, you would take your B10D, which is supplied by the manufacturer, the days of operation, 220 working days a year, the hours of operation, and the time per cycle. As you can see down here, MTTFD equals all of these together, which comes to 95 years for our mean time to dangerous failure. And then our PFHD takes our diagnostics coverage divided by our mean time to dangerous failure, which gives us a PFHD of 0, which means no failures per hour. That's what we're looking for. That would be a Category 4 device. So our PFHD as it relates to performance level, this is our probability of dangerous failures per hour and where they fall under each performance level. Performance level E would be the equivalent to Category 4. So this is where we would fall in there. And then this is where our performance level versus safety category is. So in the United States, as I said, we use categories. In Europe, mostly they use performance levels. And there is some overlap. As you can see, something that is performance level E does not necessarily have to be Category 4. It can also still be Category 3 and still meet performance level E. So things that we currently have as Category 3 in the United States, such as roto scanners, can be used in the highest type of applications. One resource we can also use is Systema software. This is a software provided free of charge by German BG. Manufacturers of safety components can provide a library with the safety values for each of their components. So basically, you would get this from ourselves, Leuze, or any other safety device company. Can give you this library, and it has all the values for each of these machines. And then you would basically just drag and drop and put a circuit together, and it just gives you basically a yes or no indication once you put everything together. Yes, this meets the performance level you're looking for, or no, it does not. So that's really it. Kind of a dry subject, a lot of calculations, but something that's very necessary to know when you're putting together a safety circuit and looking at doing a risk analysis. The topic we're going to handle next week is safety distances. A little more interesting. We're going to talk about how we can calculate our safety distances and what factors can affect those safety distances, such as depth of penetration, resolution, and different ways we can mount these. As we've said before, if you have any specific topics that you would like us to talk about or you'd like to see them in the future, be sure and let us know. Send us an email, give us a call, let us know if there's something specific that you'd like us to cover, and we'll be happy to do that for you. So we'd like to thank you for listening to our webinar, and if anybody has any questions, you can go ahead and type them into the chat box, and we'll take a look. We will see you guys next week, 2 o'clock, and we will cover safety distance calculation